Yes, the neutral and ground must be separated in the interior panel according to the National Electrical Code, or NEC. Section 250.24. A5 states that the neutral conductor must be kept separate from the equipment grounding conductors throughout the system. Section 250.24. A1 also states that the neutral conductor must be identified and insulated from the equipment grounding conductors. There are several reasons for this separation. Firstly, safety. Separating neutral and ground prevents potential electrical hazards such as ground loops and backfeeding. Secondly, the current path. The neutral conductor carries current from the load back to the source, while the equipment grounding conductors provide a low resistance path for fault currents. Thirdly, code compliance. Failure to separate neutral and ground can result in code violations and potential electrical issues. Here is a procedure that should be followed. 1. Install a grounding bar in the interior panel separate from the neutral bar. 2. Connect the equipment grounding conductors, which are green or bare wires, to the grounding bar. 3. Connect the neutral conductors, which are white or grey wires, to the neutral bar. 4. Do not connect the neutral and ground bars together in the interior panel. The water pipe and ground rod ground should be connected to the grounding bar in the feed-through panel, but not in the interior panel. The interior panel should have its own ground rod or other grounding electrode driven into the earth. The 4/0 SER cable should have 4 conductors, 2 hot wires, 1 neutral wire, and 1 ground wire. The equipment grounding conductors in the interior panel should match the size of the hot conductors per NEC section 250.122. It is important to consult with a qualified electrician for proper installation and to ensure compliance with the NEC. Let's delve deeper into the NEC requirements that mandate the separation of neutral and ground in subpanels. Understanding these requirements is crucial for ensuring both safety and code compliance in electrical installation. NEC section 250.24. A5 is a cornerstone of this requirement, explicitly stating that the neutral conductor must be kept separate from the equipment grounding conductors throughout the electrical system. This provision aims to prevent unintended current flow through the grounding system, which can lead to various electrical hazards. To further clarify this requirement, NEC section 250.24. 8.1 specifies that the neutral conductor must be identified and insulated from the equipment grounding conductors. This means that the neutral conductor, typically identified by its white or grey color, should not make any electrical contact with the grounding conductors, which are usually bare or green. The insulation ensures that the neutral current remains confined to its intended path and does not inadvertently energize the grounding system. This separation of neutral and ground is paramount for several critical reasons, each contributing to the overall safety and reliability of electrical systems. Firstly, safety is the primary concern. When neutral and ground are improperly connected, it can create potential electrical hazards such as ground loops and backfeeding. Ground loops occur when multiple grounding paths exist, creating a circulating current that can cause electromagnetic interference and pose a shock hazard. Backfeeding, on the other hand, happens when current from the neutral conductor flows back through the grounding system, potentially energizing metallic parts of equipment and creating a dangerous touch voltage. Secondly, the current path is a fundamental consideration. In a properly wired electrical system, the neutral conductor is designed to carry the return current from the load back to the source. The equipment grounding conductors, on the other hand, are intended to provide a low impedance path for fault currents such as those that occur during a short circuit. By separating these two functions, the system ensures that fault currents are safely conducted back to the source, tripping the circuit breaker and preventing an electrical shock. Thirdly, code compliance is essential for legal and safety reasons. Failure to separate neutral and ground can result in code violations, which can lead to fines, project delays, and potential liability in case of an electrical incident. Adhering to the NEC requirements ensures that the electrical installation meets the minimum safety standards and is in compliance with local regulation. To ensure proper separation of neutral and ground in the interior panel, follow this step-by-step procedure. 1. Install a dedicated grounding bar in the interior panel. This grounding bar should be physically separate from the neutral bar, with no electrical connection between them. 2. Connect all equipment grounding conductors, which are the green or bare wires, to the grounding bar. These conductors provide a path for fault currents to return to the source, tripping the circuit breaker and protecting against electrical shock. 3. Connect all neutral conductors, which are the white or grey wires, to the neutral bar. These conductors carry the normal return current from the load back to the source. 4. It is crucial to avoid connecting the neutral and ground bars together in the interior panel. This separation ensures that the neutral current remains isolated from the grounding system, preventing potential hazards. It is important to understand the proper connection of water pipe and ground rod grounds in relation to the feed-through panel and the interior panel. The water pipe and ground rod ground should be connected to the grounding bar in the feed-through panel. This connection establishes the solid grounding electrode system for the entire electrical service. However, it is critical to note that these grounds should not be connected to the grounding bar in the interior panel. The interior panel should have its own dedicated grounding electrode system, typically consisting of a separate ground rod or other grounding electrode driven into the earth. This independent grounding system ensures that the interior panel is properly grounded without creating a direct connection between the neutral and ground. The 4/0 SCR cable used to feed the interior panel typically consists of 4 conductors, 2 hot wires, 1 neutral wire, and 1 ground wire. The 2 hot wires carry the electrical current from the source to the load. The neutral wire provides a return path for the current, and the ground wire serves as a safety conductor to carry fault currents back to the source. It is crucial to ensure that all 4 conductors are properly connected and terminated in both the feed-through panel and the interior panel. The size of the equipment grounding conductors in the interior panel must comply with NEC section 250.122, which specifies that the grounding conductors should match the size of the hot conductors. In this case, since the hot conductors are 4/0, the equipment grounding conductors should also be sized accordingly to ensure adequate fault current carrying capacity. The NEC provides detailed tables and guidelines for determining the appropriate size of grounding conductors based on the size of the hot conductors. While this video provides valuable information on separating neutral and ground in subpoles, it is essential to consult with a qualified electrician for proper installation and to ensure compliance with the NEC. A licensed electrician has the expertise and knowledge to assess the specific electrical system, identify potential hazards, and ensure that the installation meets all applicable codes and regulations. Moreover, electrical codes and regulations can vary depending on the location, so it is crucial to consult with local authorities to ensure compliance with all applicable requirements. A qualified electrician can provide guidance on the specific codes and regulations that apply to the electrical installation and ensure that all work is performed in accordance with those standards. In addition to the NEC requirements, it is important to consider other factors that can affect the proper separation of neutral and ground, such as the type of electrical system, the grounding electrode system, and the presence of sensitive electronic equipment. A qualified electrician can assess these factors and make recommendations for ensuring optimal performance and safety. Furthermore, electrical work can be dangerous, and it is always best to leave it to the professionals. A qualified electrician has the training and experience to perform electrical work safely and efficiently, minimizing the risk of electrical shock, fire, and other hazards. Attempting to perform electrical work without proper training and experience can be extremely dangerous and can lead to serious injury or death. In summary, separating neutral and ground in subpoles is a critical safety requirement that must be followed to prevent electrical hazards and ensure code compliance. By understanding the NEC requirements, following the proper wiring procedures, and consulting with a qualified electrician, you can ensure that the electrical system is safe, reliable, and in compliance with all applicable regulations. Let's further discuss grounding electrode systems and their role in ensuring electrical safety. A grounding electrode system is a network of interconnected grounding electrodes that provides a low impedance path for fault currents to return to the source, tripping the circuit breaker and protecting against electrical shock. The NEC specifies various types of grounding electrodes that can be used including ground rods, metal water pipes, and concrete encased electrodes. The selection of the appropriate grounding electrode system depends on several factors such as the soil conditions, the size of the electrical service, and the local code requirements. In many cases, a combination of grounding electrodes is used to achieve the required grounding impedance. Ground rods are the most common type of grounding electrode and are typically made of copper or copper-clad steel. They are driven into the earth to a depth of at least 8 feet and are connected to the grounding system using a grounding conductor. Metal water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet and are not insulated from the earth. Concrete encased electrodes, also known as UFA-grounds, are typically used in new construction and consist of a bare copper conductor encased in concrete. The grounding electrode system must be properly sized to handle the potential fault currents. The NEC provides detailed tables and guidelines for determining the appropriate size of the grounding conductors and electrodes based on the size of the electrical service. In addition to the grounding electrode system, it is important to ensure that all metallic parts of the electrical system are properly bonded together. Bonding is the process of connecting metallic parts of the electrical system to create a common ground potential. This helps to prevent voltage differences between metallic parts, which can create a shock hazard. The NEC requires that all metallic parts of the electrical system, including metal enclosures, conduit, and equipment, be bonded together using bonding jumpers or other approved methods. Bonding jumpers are typically made of copper wire and are sized according to the size of the circuit conductors. They are used to connect metallic parts that are not already in direct contact with each other. In addition to bonding, it is also important to ensure that all electrical equipment is properly grounded. Grounding is the process of connecting electrical equipment to the grounding system to provide a low impedance path for fault currents. Grounding can be achieved by connecting the equipment grounding conductor to the equipment enclosure or by using a grounding plug or a receptacle. The NEC requires that all electrical equipment be grounded unless it is double insulated or listed as ungrounded equipment. Double insulated equipment has 2 layers of insulation between the live parts and the user, which eliminates the need for grounding. Ungrounded equipment is typically used in specific applications where grounding is not practical or safe. In such cases, the equipment must be clearly marked as ungrounded and must be used in accordance with the NEC requirements. Let's explore the concept of impedance in grounding systems. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. In grounding systems, low impedance is crucial for ensuring that fault currents can quickly and safely return to the source, tripping the circuit breaker and protecting against electrical shock. The impedance of a grounding system is affected by several factors, including the type of grounding electrodes, the soil conditions, the length and size of the grounding conductors, and the presence of any ground faults. To minimize the impedance of a grounding system, it is important to use high-quality grounding electrodes, ensure that the soil is conductive, use short and large grounding conductors, and promptly address any ground faults. Soil conductivity is a measure of how well the soil conducts electricity. Soil conductivity is affected by several factors, including the moisture content, the mineral content, and the temperature. In general, moist soil with a high mineral content is more conductive than dry soil with a low mineral content. To improve soil conductivity, it is possible to add water or soil amendments such as bentonite clay to the soil. However, it is important to consult with a qualified electrician or geotechnical engineer before making any changes to the soil. The length and size of the grounding conductors also affect the impedance of the grounding system. Shorter and larger grounding conductors have lower impedance than longer and smaller grounding conductors. The NEC specifies the minimum size of grounding conductors based on the size of the circuit conductors. It is always a good practice to use grounding conductors that are larger than the minimum size required by the NEC. Ground faults occur when there is an unintended electrical connection between a live conductor and the grounding system. Ground faults can be caused by damaged insulation, loose connections, or equipment failures. When a ground fault occurs, current flows through the grounding system, which can create a shock hazard. To protect against ground faults, it is important to use ground fault circuit interrupters, or GFCIs. GFCIs are devices that detect ground faults and quickly interrupt the circuit, preventing electrical shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. In addition to GFCIs, it is also important to regularly inspect the electrical system for any signs of damage or wear. Damaged insulation, loose connections, or corroded grounding electrodes can increase the impedance of the grounding system and increase the risk of electrical shock. If any problems are found, they should be repaired immediately by a qualified electrician. The NEC provides detailed requirements for grounding and bonding electrical systems. It is essential to consult with a qualified electrician and adhere to all applicable codes and regulations to ensure that the electrical system is safe, reliable, and in compliance with all applicable standards. This discussion of grounding and bonding highlights the complexity and importance of these aspects of electrical safety. Proper grounding and bonding are essential for protecting people and property from electrical hazards. Let's delve deeper into specific scenarios and best practices related to neutral and ground separation in various electrical installations. Consider a detached garage or a building that is fed from the main residential panel. In this scenario, it is crucial to treat the subpanel in the detached structure as a separate electrical system. The neutral and ground must be separated in the subpanel, and a dedicated grounding electrode system, such as a ground rod, must be installed to the detached structure. The feed to the detached structure should consist of 4 wires, 2 hot wires, 1 neutral wire, and 1 ground wire. The neutral wire should be insulated and isolated from the ground of both the main panel and the subpanel in the detached structure. The ground wire should be connected to the grounding electrode system at the detached structure and should also be connected to the grounding electrode system at the main panel. This configuration ensures the fault currents have a low impedance path back to the source, tripping the circuit breaker and protecting against electrical shock. Another common scenario involves the installation of a generator to provide backup power during power outages. When installing a generator, it is important to ensure that the neutral and ground are properly separated and that the generator is properly grounded. The generator should have a transfer switch that allows you to switch between the utility power and the generator power. The transfer switch should be designed to switch both the hot wires and the neutral wire. When the generator is in use, the neutral wire should be disconnected from the utility neutral and connected to the generator neutral. The generator should also have its own dedicated grounding electrode system, such as a ground rod. The grounding electrode system should be connected to the generator frame and to the grounding wire in the transfer switch. This configuration ensures that the generator is properly grounded and that fault currents have a low impedance path back to the generator. In industrial settings, electrical systems are often more complex and require careful attention to grounding and bonding. Industrial facilities typically have large electrical loads, sensitive electronic equipment, and hazardous environments. Proper grounding and bonding are essential for protecting people, equipment, and processes from electrical hazards. Industrial electrical systems often use a combination of grounding methods, including equipment grounding, system grounding, and static grounding. Equipment grounding involves connecting the metal enclosures of electrical equipment to the grounding system to provide a low impedance path for fault currents. System grounding involves grounding the neutral point of the electrical system to limit voltage to ground and provide a stable reference point for the system. Static grounding involves grounding conductive objects to prevent the buildup of static electricity, which can be a hazard in certain environments. Industrial facilities also often use specialized grounding equipment, such as ground fault monitors, surge suppressors, and isolated ground receptacles. Ground fault monitors detect ground faults and provide an alarm or trip the circuit breaker. Surge suppressors protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. Isolated ground receptacles have a separate grounding conductor that is isolated from the building ground, which helps to reduce noise and interference in sensitive electronic equipment. The NEC provides detailed requirements for grounding and bonding industrial electrical systems. It is essential to consult with a qualified electrical engineer and adhere to all applicable codes and regulations to ensure that the electrical system is safe, reliable, and in compliance with all applicable standards. Understanding these various scenarios and best practices can help to ensure that electrical systems are properly grounded and bonded, protecting people and property from electrical hazard. Let's explore common misconceptions regarding neutral and ground connections that can lead to dangerous wiring practices. One common misconception is that the neutral and ground wires are essentially the same and can be connected together without any consequences. This is a dangerous misconception that can lead to electrical shock, equipment damage, and fire hazards. The neutral wire is designed to carry the normal return current from the load back to the source, while the ground wire is designed to provide a low impedance path for fault currents to return to the source. Connecting the neutral and ground wires together creates a parallel path for the neutral current to flow, which can cause the ground wire to become energized. This can create a shock hazard if someone touches a grounded metal object, such as a metal enclosure or a water pipe. Another common misconception is that it is okay to use the neutral wire as a ground wire in certain situations. This is also a dangerous misconception that can lead to electrical shock and equipment damage. The NEC prohibits using the neutral wire as a ground wire except in very limited circumstances, such as in certain existing installations where it is not practical to install a separate ground wire. In these cases, the neutral wire must be properly sized and insulated and must be connected to the grounding electrode system at the service entrance. Another misconception is that it is okay to remove the ground wire from an electrical receptacle or appliance to eliminate ground loop hum or other noise problems. This is a dangerous practice that can create a shock hazard and damage the equipment. The ground wire is there to protect against electrical shock in the event of a fault. Removing the ground wire eliminates this protection and increases the risk of electrical shock. If there is a ground loop hum or other noise problem, the proper solution is to identify and correct the source of the noise, not to remove the ground wire. There are several steps that can be taken to identify and correct ground loop hum or other noise problems. One step is to ensure that all electrical equipment is properly grounded and bonded. Another step is to use shielded cables and connectors to reduce noise pickup. Another step is to install a ground loop isolator to break the ground loop. It is important to understand and avoid these common misconceptions regarding neutral and ground connections. Proper grounding and bonding are essential for electrical safety, and it is crucial to follow the NEC requirements and consult with a qualified electrician to ensure that electrical systems are properly installed and maintained. By dispelling these misconceptions, we can promote safer electrical practices and prevent potential electrical hazards. Let's discuss the importance of regular electrical inspections and maintenance in ensuring the continued safety and reliability of electrical systems. Electrical systems, like any other mechanical system, require regular inspection and maintenance to ensure that they are operating safely and efficiently. Over time, electrical components can deteriorate, connections can loosen, and insulation can become damaged. These problems can lead to electrical shock, fire hazards, and equipment damage. Regular electrical inspections can help to identify these problems before they become serious and can prevent costly repairs. A qualified electrician can perform a thorough inspection of the electrical system, checking for loose connections, damaged wiring, overloaded circuits, and other potential problems. The electrician can also test the grounding system to ensure that it is providing adequate protection against electrical shock. Based on the inspection, the electrician can recommend any necessary repairs or upgrades to the electrical system. Regular electrical maintenance can also help to extend the life of electrical equipment and improve its efficiency. Electrical maintenance includes tasks such as cleaning electrical panels, tightening connections, lubricating moving parts, and testing protective devices. Cleaning electrical panels can help to remove dust and debris that can accumulate and cause overheating. Tightening connections can help to prevent loose connections that can cause arcing and overheating. Lubricating moving parts can help to reduce friction and wear. Testing protective devices such as circuit breakers and GFCIs can ensure that they are functioning properly and will protect against electrical shock and fire hazards. The frequency of electrical inspections and maintenance depends on the type of electrical system, the age of the equipment, and the environmental conditions. In general, residential electrical systems should be inspected at least every 3 years, and commercial and industrial electrical systems should be inspected at least annually. Electrical equipment that is subject to heavy use or harsh environmental conditions may require more frequent inspection and maintenance. It is important to keep accurate records of all electrical inspections and maintenance. These records can be used to track the condition of the electrical system, identify potential problems, and plan for future maintenance. The NEC requires that certain electrical equipment be inspected and tested on a regular basis. For example, ground fault protection systems must be tested annually to ensure that they are functioning properly. Surge protective devices must also be inspected regularly to ensure that they are providing adequate protection against voltage surges. Regular electrical inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. By identifying and correcting potential problems before they become serious, electrical inspections and maintenance can prevent electrical shock, fire hazards, and equipment damage. Let's emphasize the critical role of qualified electricians in ensuring safe and compliant electrical installations. Electrical work is inherently dangerous and should only be performed by qualified electricians who have the necessary training, experience, and knowledge to do the job safely and correctly. Qualified electricians have completed a formal apprenticeship program, passed a licensing exam, and are required to stay up to date on the latest codes and regulations. They have the skills and knowledge to design, install, and maintain electrical systems in accordance with the NEC and other applicable standards. Attempting to perform electrical work without the proper training and experience can be extremely dangerous and can lead to electrical shock, fire hazards, and equipment damage. It is always best to leave electrical work to the professionals. Qualified electricians can assess the specific electrical needs, design a safe and compliant electrical system, and perform the installation in accordance with all applicable codes and regulations. They can also troubleshoot electrical problems, make repairs, and provide ongoing maintenance to ensure that the electrical system is operating safely and efficiently. When hiring an electrician, it is important to check their qualifications and ensure that they are licensed and insured. You can check an electrician's license status with the local licensing board. You should also ask for references from previous customers and check online reviews to get an idea of their reputation. It is also important to get a written estimate from the electrician before they begin any work. The estimate should include a detailed description of the work to be performed, the materials to be used, and the total cost of the project. Be sure to ask the electrician about any potential hidden costs or fees. Qualified electricians are committed to safety and follow strict safety procedures to protect themselves and their customers. They use personal protective equipment, such as gloves, safety glasses, and insulated tools to prevent electrical shock. They also follow lockout/tagout procedures to ensure that electrical circuits are energized before working on them. Qualified electricians are also knowledgeable about the NEC and other applicable codes and regulations. They stay up to date on the latest changes to the codes and regulations and ensure that their work is in compliance with all applicable standards. They can also provide guidance and advice on electrical safety and energy efficiency. In conclusion, qualified electricians play a vital role in ensuring the safety and reliability of electrical systems. By hiring a qualified electrician, you can be confident that your electrical work will be performed safely, correctly, and in compliance with all applicable codes and regulations. It is always best to leave electrical work to the professionals and avoid the risks of attempting to do it yourself. Let's recap the key takeaways regarding the separation of neutral and ground in electrical systems. Firstly, the NEC mandates the separation of neutral and ground in subpanels and other electrical systems to prevent electrical hazards and ensure code compliance. Secondly, neutral conductors carry normal return current, while ground conductors provide a low impedance path for fault currents, and these functions must be kept separate. Thirdly, improper connections between neutral and ground can lead to ground loops, backfeeding, and energized ground wires, posing serious safety risks. Fourthly, a dedicated grounding bar must be installed in subpanels, and all equipment grounding conductors must be connected to this bar, while neutral conductors are connected to a separate neutral bar. Fifthly, grounding electrode systems, such as ground rods and water pipe grounds, play a crucial role in providing a low impedance path for fault currents and must be properly installed and maintained. Sixthly, regular electrical inspections and maintenance are essential for identifying and correcting potential problems and ensuring the continued safety and reliability of electrical systems. Seventhly, electrical work should only be performed by qualified electricians who have the necessary training, experience, and knowledge to do the job safely and correctly. Eighthly, common misconceptions regarding neutral and ground connections can lead to dangerous wiring practices and must be avoided. Ninthly, always consult with a qualified electrician and adhere to all applicable codes and regulations to ensure that electrical systems are properly installed and maintained. Tenthly, understanding these key takeaways is essential for promoting electrical safety and preventing potential electrical hazards. By following these guidelines and best practices, we can create safer electrical environments for ourselves and others. The importance of ongoing education and training in the electrical field cannot be overstated. The electrical industry is constantly evolving, with new technologies, codes, and regulations being introduced on a regular basis. It is essential for electricians and other electrical professionals to stay up to date on these changes in order to provide safe and compliant electrical services. There are many opportunities for ongoing education and training in the electrical field. Electricians can attend continuing education courses, workshops, and seminars offered by trade schools, community colleges, and professional organizations. They can also participate in online training programs and webinars. Some states and local jurisdictions require electricians to complete a certain number of continuing education hours each year in order to maintain their licenses. The NEC is updated every 3 years, and it is essential for electricians to stay up to date on the latest changes to the code. The NEC contains detailed requirements for electrical installations, and it is crucial to follow these requirements to ensure safety and compliance. In addition to the NEC, there are also other applicable codes and regulations that electricians must be aware of, such as local building codes and environmental regulations. Ongoing education and training can help electricians to develop new skills and knowledge and to advance their careers. Electricians can specialize in specific areas of the electrical field, such as renewable energy, industrial automation, or telecommunications. They can also pursue certifications in specific areas, such as Certified Electrician, Certified Master Electrician, or Certified Electrical Inspector. Ongoing education and training can also help electricians to improve their safety performance. By staying up to date on the latest safety practices and procedures, electricians can reduce their risk of electrical shock, falls, and other hazards. It is important for electrical contractors to provide ongoing education and training for their employees. This can help to improve the quality of their work, reduce their liability, and improve their reputation. Electrical contractors can offer in-house training programs, send their employees to external training courses, or provide access to online training resources. Ongoing education and training are essential for ensuring the continued safety, reliability, and compliance of electrical systems. By investing in ongoing education and training, electricians and electrical contractors can improve their skills, knowledge, and safety performance and provide the best possible service to their customers.